All right, and welcome to another video in this series on algorithm analysis. In this video, we're going to introduce little o notation, which is another asymptotic notation similar to big O notation. Not quite as commonly used, but also useful to do some comparisons between functions. We might make a comparison, say, where we might say big O of f of n kind of means less than or equal to f of n. Maybe not exactly less than or equal to. So here this is a rule of thumb. This isn't exactly 100% the interpretation, but we can use that as a quick shorthand. And then we could say big omega of f of n. That one maybe is more like a greater than or equal to f of n. And then we argued in the last video that we could then make theta of f of n is just the combination of those two then. Well, if you have something that's less than or equal to and you have something that's greater than or equal to, then putting them together, you get something that is equal. Well, this sort of analysis, this rule of thumb here, leaves open two more possibilities, and that's where we're going to get our little o of f of n. And this one we can think of as less than f of n, strictly less than. And then again, we'd get a little omega of f of n, which again, this one might be strictly greater than f of n. And so we're going to be introducing these two today, the little o and the little omega. And these are, again, just an extrapolation a little bit off of our big O and our big omega to give us the strictly less than and the strictly greater than, ruling out the possibilities of the equal to. Just a final last comment in case your ancient Greek letters aren't up to snuff. We've got the capital omega up here, and we've got the capital theta here. And then this is just the lowercase omega, which kind of looks like a W with a little tick on the end there. All right, so we can see here on the slides that we've got that same intuition that we just introduced here, that the little o means strictly slower than f of n or less than f of n, and little omega means strictly faster than f of n. So again, we've just added these two dimensions. Completing that together, we've got the sort of the rule of thumb or the cheat sheet here for our 5 possibilities that you might encounter for two functions f of n and g of n. And maybe it's worthwhile to mention as well that for any two functions, you could be in one of these 5 relationships. It's also possible that there is not one of these 5 relationships between our two functions, especially if we encounter strange functions, not good runtime functions. And so we mentioned in an earlier video, good runtime functions are typically non-negative and typically non-decreasing. And so if you've got a function that is either negative or decreasing, it might violate some of these principles, and then it might not actually fall into one of these categories. We're going to restrict our focus on well-behaved runtime functions, so we probably won't encounter any of those examples. All right, so one reason we wanted to introduce the little o notation was to add another tool to our toolkit for comparing functions, and that tool is the limit test. So here I have a quick little theorem where we present the limit test. The theorem, as stated here, requires that we have two functions here, f of n and g of n. And here I state there are two runtime functions, but I haven't actually stated specifically what I mean by that formally. But let's assume they're well-behaved runtime functions. They're monotonically non-decreasing and non-negative, at least over the range that we're interested in. So say we have these two functions, then what we want to do is we want to compare, or we want to compute the limit of their ratio. So we're going to take the ratio f of n over g of n. We can see in each of the three cases here, we're just computing that limit. So if we're going to use the limit test for anything, the first step is compute that limit. Now here we've got f of n over g of n. We could also take g of n over f of n. That's obviously just an inverse case. And usually we want to pick the, f of n over g of n or g of n over f of n, whichever one's easier to compute. That's what we're going to pick. Then if we compute the limit, so we'll break out our calculus skills and compute the limit. If the limit is, well, basically we're going to have one of three possible cases here, and so each of these three cases tells us the conclusion we can draw given that case. So the first case, if the limit of f of n over g of n is infinity, the limit test tells us we can conclude then that f of n must be in little omega of g of n. Now let's go back to our little cheat sheet here. Little omega of g of n means grows faster than. So in this first case, that means that f of n must grow faster than g of n. And that makes sense if the limit of f of n over g of n goes to infinity. The function f of n must grow a lot faster than g of n if that limit goes to infinity. Let's change that relationship around. Let's say that g of n is the faster now. Then if that's the case, then the g of n will grow much faster. It will reach infinity before f of n does. And so we get the opposite relationship. We get the limit approaching 0 now. The ratio will approach 0 as f of n becomes dwarfed by g of n. And if that were the case, then we said that was the case where g of n grows faster, or vice versa, where f of n grows slower. In that case, we get the big O relationship. F of n is in, little o of g of n. Okay, so that's the second case. And then the third case is what happens if we don't have one of them growing faster than the other. Let's say they're growing at the exact same rate. Maybe they're the exact same function, f of n is g of n, then we know this ratio would be 1. Well, here in case 3, that says a constant for some non-zero c. So if we get 1, or we got a different constant, say 2 or 10, then we would say that these two functions grow at the same rate, and that rate, when we say they grow at the same rate, we say that's a theta relationship. And most often, that's what we're trying to look for when we're doing the limit test, is the theta relationship. We want the outcome to be a non-zero constant then. When we compute the limit of their ratio, we want it to be a non-zero constant. And that will get us in the theta category. Otherwise, we might be comparing two functions. Maybe we don't know how they relate to one another, and we want to know which one grows faster than the other. Well, that's when the limit test again might come in handy. Got a little proof sketch here, but I think I've gone over each of these in our discussion here, simply stating that if that limit goes to infinity or 0, then we have reason to believe that the relationship holds, the one that we're interested in. So let's go ahead and take a look at an example here. And the example that I want to look at is this one. All right, so the function we're interested in here is 6n plus 6. That's sort of our f of n. And we want to show that this function is in theta of n. Now, the way we're going to do that, to use the limit test, is we're now going to want to compute the limit of the ratio between these two functions. The two functions are this one here, f of n 6n plus 6, and our g of n then is just n. Okay. So that means we want to compute the limit as n goes to infinity of our f of n over g of n, which will be the limit, again, as n goes to infinity, of our 6n plus 6 over n. All right, so this is what we want to compute. Now remember, in doing this, it's going to be convenient for us to split this limit up. So let's continue here. 6n over n plus 6 over n. And it's here where, again, maybe we can do some simplification to make it pretty easy for us to see here. This is going to be the limit n goes to infinity of just 6, it's the first term, plus the limit n goes to infinity of 6 over n. Now, of course, the first one here goes to 6. The second one goes to 0. So in total, we get a 6. And this is the type of calculation we might be trying to get if we want to establish this bound. Now remember, by the limit test, since this is a constant and it is greater than 0, it's non-infinity, then that means the relationship we've established between these two is a theta relationship. Okay, so not too difficult. That was a pretty straightforward limit to calculate, but this is just to illustrate again how the limit test is going to work. Okay. Notice maybe quickly here we could have also computed g of n over f of n. If we did, the logic gets a little bit trickier. So it's convenient to put it this way. It was easier to split the function up and compute the limit. Okay, all right. Let's take a look at another one here. Log n grows slower than n. So if we want to do that, again, little o means slower. If we want to do that, we're going to compute a limit. So let's go ahead and do that. We're going to get our limit. We're going to take log n all over n. So computing this limit now, some of us, maybe our calculus is strong enough, maybe we've reviewed this material before, so we are already familiar with this. We might already know what this limit is. Our intuition might be strong enough to say, oh, I know what that is. If you do know what it is, that's great. If not, well, let's practice our limits. Let's see what we can do here. Now, one thing we're going to notice here is that in this case, this function, log n, goes to infinity, and this function here, n, goes to infinity as well. So we're in a case where we have infinity over infinity. And this is usually a problematic case. There's a number of problematic cases, multiplying infinity by infinity, and subtracting it. There's a couple places where infinity gets messy. Infinity divided by infinity, our instinct might be, hey, that's 1, but the truth is that's not always true. Sometimes infinity divided by infinity is infinity, sometimes it's 0, sometimes it's 1, and sometimes it's any other constant, and as we saw in our limit test possibility. So it's here where we might say, okay, back to calculus books, what do we have in our toolkit for calculus? Well, if we've got infinity over infinity, that's one of the cases where we might want to use our L'Hopital's rule. Okay, now remember what L'Hopital's rule said is if the limit exists, then if we can take the first derivative of the top and the first derivative of the bottom, if we take the limit of that ratio, then that will be the same as the limit of this ratio. So taking the derivative of the top and the derivative of the bottom. All right, so that means we're going to need to, again, practice our calculus a little bit here. So we're going to get another limit as n goes to infinity here. And what are we going to get on top? Well, the top, we're going to get the derivative of the top. Now, I'm going to be a little bit careful here. I'm going to write it as c over n. Where c here is the constant that pops out. Now remember, the log here, I haven't told you what log it is. And if I don't tell you what log it is, I probably mean 2. So if I've got log base 2 here, then actually, when we take the derivative, we're going to need the natural logarithm. So we're actually going to get a constant that pops out here when we're trying to convert this log from base 2 to base e, the natural logarithm. And we're going to get out something like the natural logarithm of 2, some constant. That constant's not going to matter for us in our calculation. And I've gotten in the habit of, when constants don't matter to me, I just give them names like C and slough them away. That way I don't have to calculate what it is and figure out what that value is. Occasionally that constant is going to matter. I might need to know, is that bigger than 2 or less than 2 or something like that. If that's the case, I might need to keep it as it is, but in this case I probably don't. So I'm going to take the derivative here and I'm just going to write it as C over n. And maybe that's not going to be important. We didn't take the derivative of the bottom here, but that's got to be the simplest derivative to take. That one's just going to be 1. So we can see, and maybe we'll just bring it down here to make it easier. This is the limit of C over n. Well, this is a constant. This goes to infinity, so that's pretty easy to see that this is a 0. Okay. Well, when we arrive at a 0 in our relationship, remember that meant the bottom function, the g of n, grew much faster than the top function. So in this case, we've shown the relationship we wanted to. Log n is in little o of n, and remember, our cheat sheet, if we want to remember what that means, log n is less than n in growth rate. So this rule, not mathematically correct. But that's how we maybe interpret this relationship between log n and n. That log n is less than n, at least as n gets really big, and maybe with a constant out front to inflate n. But for our relationship here shows that log n is less than n. All right, to complete this video, I would like to do a simple exercise here. We're probably going to use the limit test here as well, but we might use some other techniques as well. The goal here is, say you've got a collection of functions here. Maybe these are functions that represent the runtime of a particular algorithm or a collection of algorithms you have. Maybe you're comparing a collection of algorithms for a problem, and you want to know which one is best or what how these algorithms compare to one another. So to do that, you've got these runtime functions, and we now want to put them in order of asymptotic growth rate. So we want to basically find out which ones grow the slowest, which ones grow the fastest, and then use that to put them in some order. Okay, so here we have our 6 functions, and probably the first thing we want to do is for each of these functions, we want to simplify it a little bit or find the theta class that it belongs in. And then we can compare the theta classes for each function. That makes it a little bit easier on us than trying to, say, compute the limit of f of n over g of n. These are nasty looking functions. So for instance, this function here, it might not be too hard for us to make a guess here. Let's start by just making a guess. What do we think the theta bound for this function might be? Now, remember, this is going to be a polynomial, and the polynomial is always going to be dominated by its highest degree term, or the term with the highest exponent, and we can see that the highest exponent will be 2 times 2 here, or 4. So our guess might be n to the 4th for this particular function, f of n. Now, we could go ahead and try and prove that using a limit test. And there's maybe more than one way we could do that. We could, I personally would probably use the definitions from the previous video, but we could use the limit test. We could expand this open. But we might find that there's a lot of steps, a lot of algebra involved in that, and so we might want to see if we can maybe approximate this first of all. Now remember, last day, by increasing this to an n squared in the last video, we're able to take this binomial and turn it into a monomial, which makes the raising it to the exponent a lot easier, and so that might be an easier technique to tackle this one. Taking a look at the next one, again, same thing here. If we multiply out, that's not going to be too hard to do. So we're going to get here maybe an n squared log n minus a 3n log n. And we can see, well, this is a negative term, but this is the more dominant term. So sure enough, this is the term for our theta class. Okay. So again, we might start thinking to ourselves, how do these two relate to one another? And maybe let's just do a quick little check here. If we did an n to the fourth all over n squared log n, we can quite easily see that these two are going to cancel out, and we're going to get an n squared over log n relationship. We just did a limit test to tell us that log n grows slower than n, so log n must also grow slower uh, than n squared. So again, a quick limit test on the side might allow us to see that. Okay, so continuing along here, what about this one? This one maybe is pretty easy too. The over 2 doesn't do anything for us, neither does the plus 11. So this one is in theta of n. Okay, so we might, again, keeping track of all of these. All right, a to the log n can be a little bit tricky, so let's maybe make a little extra space down here. To note that 8 to the log n, this is a base 2 log, so if we want to know what this is equal to, we might actually know there's a rule. We can swap this n with the 8 here. But I'll maybe make it a little bit easier for us to see this. We can write this as 2 to the 3 all to the power of log n, which we can also write as 2 to the log n all to the 3. Now, of course, 2 to the log n, we should know what that is equal to. That's just equal to n raised all to the third power. We get n to the 3. So simplifying this one here, we can see that this should be an n cubed function. Okay, so that's our n cubed function. What do we have here? This log function, maybe our experience with the log function we worked with already is going to help us here. That this one is actually in theta of log n. Okay, this one's in theta of log n. The 4 and the 4 and the plus 9 don't actually do anything for us here. So that leaves us with our last two cases here. Again, we have 2 to the log, just like in our scratch work we did there. This is log base 2, so these are the same base, so they cancel each other out. So this one's actually pretty simple. This one's just n squared. It's exactly equal to n squared after we cancel out. So saying this is theta n squared is pretty straightforward. And then the last one here is also a little bit messy, a little bit tangled, but not too much effort allows us to see that this last one is going to be in big theta of n to the 4 all over log n. So let's maybe take a quick look at what those possibilities are going to be here. Let's start with the slowest growing function. It looks like the slowest growing function, we had no constant functions, so it looks like we have here j as our first function. So I'm just going to write j here. J is less than what? The next function. So that was j, our log n. Okay. Now that we've used log n, we want to find the next one in our list. And now most of these are polynomials. A few of them have logs in there, and we're going to need to be careful with them. But the next polynomial on our list, it looks like we have an n, and that is function h. Okay, so h is next. All right, so once we have function h, that's crossed out, that's an n. Now it looks like we have a couple candidates here. We have n squared, and we have n squared times log n. And maybe we don't know how those two relate to one another, and so we need to do a little bit extra work. If we want to, we can quickly throw them in a limit. If we take n squared log n, divide it by n squared, we'll notice the n squared cancel out. That leaves us with still a log n on this function. So this must be the faster growing function. N squared grows slower than n squared times log n. Multiplying by log n makes it greater. So and it looks like the next function we have coming up is k. And then the next one, what was it? G. So we took out our n squared. Now we also have, it looks like we have 3 more functions remaining. We have this n cubed, and then we have the 2 with the n over 4. It looks like n cubed is probably going to be our next one. So that one's I. And then again, we need to deal with these two with the n over 4. And let's maybe look at this one down here. We said this one was n over 4 divided by log n, whereas this one's just straight up n over 4. And so maybe we have the same relationship we had before, except here where we were multiplying by log n, that made us bigger. Down below here, we are dividing by log n, that makes us smaller. So that means L is actually next. And then the final one is F. So that puts these in order. Maybe we could formalize that a little bit more by running the limit test on some of these, or using the definitions to help prove formally these relationships. But this helps build our intuition, helps us look at runtime functions maybe quickly and put them in order of their asymptotic growth rate, so we can use that to quickly compare the runtimes of two algorithms. All right, this is going to be the end of this video. And in my next video, I'm going to take some of these skills and we're going to move them on to the next level. We're going to apply them to iterative algorithm analysis. So we're going to start looking at some pseudocode and applying these techniques to analyze the pseudocode to measure how many operations that pseudocode will take on a particular input. All right, thank you, and we'll see you in the next video.